Okay, today I'm going to try to discuss some problems from some past papers, past exams. So this is the problem discussion one, actually. Okay, so I picked this question from 2019, 2020 CAT one. So the question is, determine the stereochemical relationship between the two molecules A and B given below. And say, support your answer by giving RNS configuration of the chiral centers of them. Clearly indicate the priorities of groups according to Kahn-Ingold-Prelog rules. So you have two molecules. The first thing you need to do is to figure out whether you actually have any chiral centers, because for you to assign RNAs, you have to have chiral centers or stereo centers. For that, you have to have 4 different groups, and both molecules have on both carbons 4 different groups. And so then you have 2 stereo centers on each molecule A and B. So then the first task is to, before you determine the relationship between these two, the first task is to assign RNS configurations. And to assign the RNS configuration, the first thing is you have to assign the priorities according to the Kahn-Ingold-Prelog rules. And these rules are based on the atomic numbers. The higher the atomic number, higher the priority. So then after you assign the priorities, then you can determine the RNS, and then we can see what is the relationship between these two molecules. Okay, just to refresh your memory, to remind you how to assign these RNS configurations, like I took this example, glyceraldehyde, something we actually discussed in the class also. So that this carbon right here is a stereo center, but this one is not. This one has 2 hydrogens. So therefore, no 4 different, it does not have 4 different groups. So therefore, this carbon is not a stereo center. So then if you draw the molecule kind of, expand the expanded version, and what they have drawn here is the R glyceraldehyde, and I hope you remember the meaning of these wedges. The dark wedge means it's coming towards you, and the dashed wedge is going away from you. And the solid lines, they are on the plane of this the screen, or if you drew the molecule on a paper, so then they will be on the plane of the paper. So now when we assign, so this particular molecule, oxygen has the priority number 1 because oxygen has a higher atomic number. Then you have these 2 groups where you have the hydroxyl group and the aldehyde. So then you go along that carbon chain. So you meet this, you meet this carbon right here, and so that carbon. So then when you compare them, so this carbon is attached to 2 hydrogens, and this carbon is actually, when you have a double bond, if you remember, so it's like attached to 2 oxygens. So therefore, obviously this group gets higher priority than the other one, the hydroxyl attached carbon. So therefore, this will be priority number 2, and this is priority number 3, and hydrogen is obviously priority number 4. So then the way we assign this RNS configuration is, what you need to do is you hold or you keep the least priority group away from you. So you have to imagine like you have this molecule in your hand and you hold the molecule with the least priority group, or the group with the number 4 priority. Here it is the hydrogen. So you hold the molecule from hydrogen, or you keep the hydrogen away from you in the back. Then you look at the molecule. So when you look at that means, you look at the molecule from this direction, right? So then you will see the hydroxyl group number 1 priority here, and the number 2, the aldehyde, and the number 3, the carbon attached to the hydroxyl group. So then what you do is you draw a line connecting these groups 1, 2, 3, like 1 through 3. So you don't consider the number 4 one. It's kind of removed. You keep it away. Then you consider only the other 3 which are left. Which have priority number 1, 2, and 3. Then you draw a line connecting them, and if you see the priority is changing clockwise, then it is R. If the priority is changing anti-clockwise, then it is S. Okay, if you go back to this, the molecule given in the question, so what we need to do is first assign the priorities, and if you consider this carbon, so bromine definitely gets the number 1, and then hydrogen is definitely number 4. It is the least one here. And so then we have CH3 and another. So the next carbons, as I explained to you during our unit 1. So if you have common, if you have the same atom on 2 different groups, so you have to go along the chain until you can distinguish them. So the next, if you compare these 2 groups, so you have a carbon. So you have a carbon, that is the first atom. So then that's equal. Then you go to the next atom. So this carbon, it has 3 hydrogens attached to it, but this carbon has carbon, oxygen, hydrogen. So therefore, this should be the number 2. And then this should be number 3, and you have number 4 in the back. So let me erase all these and put just the numbers so that it'll be clear for you. So this is not that difficult. Okay, so this will be, I don't know, my notepad is not working properly. Number 1, number 2, number 3, and number 4. So then how do you assign this configuration now? So now you have number 4 in the back already. Now then you connect these. So they are, in the anti-clockwise manner. So then therefore this center is actually S. Okay, then how about the other one? So let me erase this again, just for the clarity. Okay. Right. Then, so this one, number 4, and oxygen has the highest priority, and this will be number 2, and this will be number 3. And so I'm not going to explain again. So I hope you understand. And then what you need to do is you have to look at, from this side, because you have to put the 4 in the back. So then when you look at from that side, so then if you can draw that, it's like the CH3, when you put the hydrogen in the back, if you look at from this side, CH3 is coming towards you. So that means, you have the bigger group, I'll put this one as the R, which has the number 2 priority. And as the CH3 is coming towards you, then if you look from the side, it's actually going to your left, and the OH is going towards to your right when you look from the side. I hope you can understand that. Then you have number 1, number 3, right? So then if you connect them, so that is also going anti-clockwise, 1, 2, 3. That is also S. Therefore, this is also S. And so that's done. So then let's go to the second molecule. So number 1, 2, 3, and 4. And so you hold the 4 in the back and you look at the molecule from this side. That means it'll be like, so OH OH and CH3. Okay, so then you have, okay, no, let me draw this again. So when you look at from this side, what you have is, this kind of arrangement. So I'm going to put this one as R, the bigger group, which has the number 2 priority. And then on your right side, when you look from this side, on your right side, you will have OH, because it's going away from the screen, and you have CS3 on the left side. Then this is 1, and this is 3. And so as you could see, okay. So then if you connect them, so this is 1, 2, 3 in the clockwise manner. So this is R. So then this center is R. And so if I look at this, if you pay attention to the other carbon now, so this is number 1, and the other group becomes 2, and this is 3, and this is 4. 3, 4. Then you draw that again, keeping the number 4 in your back. That means you have to look at the molecule. It's difficult to change pens. You look at the molecule from this end, and if you look at the molecule from that end, so you will have this kind of situation. So this is the R group, which has this second priority, and CS3 is coming towards you on the plane. So therefore, if you look at from the side, it is on the right side, and the bromine is going down. So this is 1, and this is 3. So then again, it is R, 1, 2, 3. So okay. So if you connect them, so it's again R. So therefore, this is R. So now, so if you look at the molecule, if you go back, just now we kind of figured out the S and R of each stereocenter. So then if you go back, so this was S, this is S, this is R, and this is R. So then what is the relationship between these two? So S has become R, S has become R. So therefore, these are enantiomers or mirror images, because all the stereocenters have been inverted. So then these are enantiomers. So what if we had a different situation, like for example, this is just hypothetical, okay, not relevant for this molecule. If this was S, then they become what? Diastereomers. Okay, that is just another possibility. If all the stereocenters have been inverted, and the stereochemistry S goes to R, S goes to R, or R goes to S, R goes to S, then since both are inverted, these are enantiomers. But if you have 2 stereocenters or more than 1 stereocenter, and only one is changing and one remains the same, then they are diastereomers. So that also another possibility. Okay, I hope you understood how we approach this problem, and how we, what is the strategy, and how you determine the SNR first, and then how we compare the overall molecules. Okay, the next question, it says the following compound X, so you don't have to worry about the name. So it's being labeled as X, undergoes E2 eliminations. Already they have mentioned it's the E2 elimination. And so we know what is E2 elimination. With alcoholic potassium hydroxide. Alcoholic potassium hydroxide means potassium hydroxide in ethanol. So the solvent is ethanol and you have potassium hydroxide, which is the base. We know that for elimination reactions, we need a base to take care of that hydrogen. Okay, the first part is to draw the two chair conformation of X. So because this is cyclohexane, and cyclohexane has conformations, the chair conformations. So any cyclohexane molecule has two chair conformations, so then they're asking for the more stable conformation and the least stable conformation or less stable conformation. You have to draw within these boxes. So just to remind you, I'll give you give you some tips on how to draw this given molecule, because this does not show any conformation of the chair shape of the molecule. Then how do you convert this drawing, the given drawing, to chair conformation? So let's take this as an example where you have these two substituents, hydroxyl and the chloride, and the hydroxyl is coming up. So this dark wedge means hydroxyl is coming up and the dashed wedge, chlorine, is going down. So they're like trans to each other. So the number one step you need to follow is, so you have to, when you have these substituents, so you can number these atoms in the ring. So you have the ring, so you number the atoms on the ring as you wish. It doesn't really matter. You will understand why we need to do this. Because when we draw the chair conformation, we need to put these substituents at the right place, where they were in this given drawing. It's a normal drawing. So therefore, you can put the numbers anywhere you want, in the direction you want. It doesn't have to be the the UPAC numbering. So don't worry about that. You should just put some numbers so that we'll have like a correct address for these substituents, when you transfer these substituents to the chair conformation. Then, depending on the wedges, you label them as up, down. So label the wedges up, down. So the hydroxyl is coming up and chlorine is going down. So that is the next step you need to do. Okay, so then what you do is you draw the chair conformation, one of them. So we know that there are two chair conformation, they undergo this ring flip. And so you draw one of them. It doesn't matter which one you draw first. And then you number the chair conformation the same way as you labeled them before. And then you put the, we know that hydroxyl, hydroxyl was at the number 1. So then you put the hydroxyl, the first, then you actually find in the number 5, step number 5, so you introduce the substituents. You introduce the hydroxyl at the first one, first carbon, and we know hydroxyl is going up. So therefore, it should be equatorial. So here, depending on the ring, the conformation, here, the equatorial or the axial might be going up. But in this conformation, equatorial is going up. The axial one is actually going down. So therefore, you put hydroxyl as the equatorial position. Then we know that the third position has the chlorine, and in this ring, the third carbon, equatorial one is going up, and axial one is actually going down. So therefore, we put the chlorine as the axial because chlorine needs to be down. So it's not like, remember, so there is no such thing as wedge is always axial or dash is always equatorial. It is not like that. The meaning of that is, in the overall, the molecule, the OH should be coming up, chlorine should be going down. So this OH coming up should be taken care of by equatorial or axial, depending on the conformation. And the chlorine going down also should be shown as axial or equatorial, depending on the ring shape or the ring. the conformation. So then, so you can draw the other conformation. So the two rings, I'll show you a shortcut how to draw these two conformations easily without any confusion. So now we drew that one. So hydroxyl is coming up, chlorine is going down. So then when you do the ring flip, and we know that equatorial positions become axial. So this become axial, and this axial position became equatorial. So now, so that is the other ring shape, and so the left one is actually more stable. I mean, that's why it's kind of the equilibrium is towards the left one, because of the hydroxyl will have more steric clash, and so therefore hydroxyl in the axial position may not be that stable. Okay, so that's how that those are the steps that you have to follow when you try to draw the chair conformations from a given drawing of a cyclohexane molecule. Okay, then how do we do this ring flip? So it's very very easy to do. So there are only two chair conformations. So one of them, to draw one of them, so you draw two lines parallel to each other like this. You have to kind of remember this, the way you draw shape parallel. And so don't draw like this. So there you have to draw them at an angle, because see these lines coming from the you have to have that chair type, the chair shape should be maintained. So that's why we draw this. The first step is to draw these angle lines, and in this manner. Then what we do is draw the blue lines as shown here. So that is the next step. So you draw this way like that, and then you combine these. You combine these to get the one of the chair conformations. So then you get this. It's very easy. So it's, there's nothing to explain here. Just you can follow the steps. So the other one will be it's opposite, like the mirror image of the above one. So you draw the lines in the opposite direction, kind of still have to draw them tilted, and then you draw the blue lines and you connect them. So then you get the flipped ring as shown here. So that's very easy steps to follow when you do the ring flipping. Okay, now let's draw the two chair conformations of X. Okay, let's first draw. Okay, let me get a different color here. So first, one chair conformation, you drew two lines. So that's how we do that. Then you draw another line here, another line here. Then you combine them. So, okay. So then how do you draw the other one? So you draw the two lines in the opposite direction, and then you extend it. So this way, then you combine them. Okay, so that is a flipped ring. Okay, so now we have three substituents to draw. And as I mentioned before, maybe, we can put numbers 1, 2, 3, 4, 5, and 6. Then starting from here, maybe we can put the same numbers 1, 2, 3, 4, 5, and okay. So I was saying, you can label the, number the ring so that we can transfer the substituents easily. So then you'll do the same numbering here. So on, on both rings, I hope this is being recorded. Okay, so then the trimethyl or the tertiary butyl group. So this is the tertiary butyl group. And so you will see this tertiary butyl group, throughout this course. It's a very common kind of functional group, or a or a substituent. And so it is coming up. And when we draw this these chair conformations, here we have these are the two axial and the equatorial the positions. So you have these, that's something you have to know, if you so you have to have 3 axial and 3 equatorial positions all the time. And sorry, that is wrong. So be familiar with these, different conformations, how we have these different equatorial and axial positions. You have this. And okay, so then the tertiary butyl group is actually coming up on this molecule. So what you need to do is, so you put the carbon trimethyl, the carbon source, the tertiary butyl group here, and then the chlorine, which is next door to that, which is on the next carbon, the neighboring carbon, should be coming up. So that means it should be on the equatorial position. So that is chlorine. Then you have the methyl group, another methyl group, which is going down. That is on the 4th carbon, and it should be on the axial position because it's going down. Okay. Okay, so now we have transferred these 3 groups to this group, and we'll see the other one, like how the groups should be attached to the other one. Okay. So now in the ring flip, all these axial positions become equatorial, and equatorial becomes axial. And so then okay, so when we do the ring flipping, so these, even the other conformation, the flipped conformation also should have the same stereochemistry. This tertiary butyl group should be coming up, and the chlorine also coming up, and the methyl should be going down. So then in the flipped conformation, the tertiary butyl group attached to carbon, for it to be coming up, now it should be in the equatorial position. So here we have the tertiary butyl group, as you can see. And okay, so then so we put the tertiary butyl group here on this conformation as CMA3 here. Then the chlorine should be going up, and so now on the flipped one, so we put chlorine here. And so because it should be coming up, now it is on the axial position. And on the 4th carbon, we have methyl, and it should be going down. Now it should be, in order for us to show it as going down, it should be the equatorial position. So actually, I drew these two molecules without giving, without considering which one is the most stable or not. So what you need to do is, if you can, say, if you're not sure about, which one you can draw on the most stable or the less stable conformation. So you draw these molecules on a separate paper, like, your scrap paper, and then transfer the answers. But okay, let's see from the 1 and 2, which one is most stable. We know that, this is huge group, tertiary butyl group is huge. Then it will have 1,3 diaxial interactions with these hydrogens. So then having tertiary butyl group and also methyl group, because that methyl, this one also will have 1,3 diaxial 1,3 diaxial interaction with these two hydrogens here, these hydrogens here. So then this is actually number 1 will be the least stable. So I have drawn on the wrong side, but I actually did not consider that one when I started drawing these. So therefore, this is the least stable conformation, and this is the most stable one, because this one does not have, this one has only chlorine, the 1,3 diaxial interaction only with the chlorine, but the number 1 conformation has 1,3 diaxial steric clash between tertiary butyl, which is the biggest group here, with the axial hydrogen, and so also methyl also has that. So then therefore it is too much under too much steric crowding, steric clash. So therefore that one will be the least stable, and this will be the most stable conformation. So which conformation so then the next question is, which conformation undergoes the E2 elimination, and explain why. So in the E2 elimination, if you remember from our the session on eliminations, I think the session number 5. So E2, for E2 elimination to occur, so you need to have this arrangement. Sorry. You need to have this arrangement. Can't draw today. So the leaving group and the hydrogen, so base will take care of the hydrogen, and so this will be broken onto this one to make the double bond, and this is the leaving group. And see, these should be anti to each other. That is one requirement, and they should be on the same plane, on the same plane. So that is one, that's a another requirement. So then just go back and see which one actually fulfills that requirement. So then we have the chlorine, that is the leaving group we have. So then that, if that is the alpha position, and so then we have to look for beta hydrogen. So we have 2 hydrogens here, and actually 1 hydrogen here as well. So then the E2, and also the other thing we need to consider is E2 mechanism will give you the Zaitsev product, which is the most substituted alkene. So then to get the most substituted alkene, so then you have to make the double bond here, right? So if you make the double bond here, so you won't have the most substituted. So therefore this, in the abstraction of this hydrogen, may be preferred to give you the most substituted alkene, according to the Zaitsev rule. But before that, the anti-periplanar arrangement is very important. So we'll see which conformation gives you that anti-periplanar arrangement. So the chlorine, so this should be the one, because we have chlorine being on the axial position. Then you have axial hydrogen here. So these two have, let me Let me erase some of these so that, you know, we can have some kind of clarity here. Okay, so this chlorine and this hydrogen, so they're anti-periplanar to each other, so they're on the same plane and anti to each other, therefore they can undergo the beta, you know, so the E2 elimination. And this hydrogen also is anti-periplanar with chlorine, and also if this hydrogen is, you know, kind of taken by the base and you create the double bond here, and it will be the most substituted alkene according to the Zaitsev rule. So we prefer to make the most substituted alkene. So therefore, the answer is which conformation undergoes the E2 elimination is the answer is the most stable one. And you drew the excuse me, you draw the conformation again and show this anti-periplane arrangement, and also explain there are two possibilities. There are two beta hydrogens, which are anti with the chlorine, but this one, the hydrogen on the carbon number 1 will be preferred because it will give you the most substituted alkene according to the Zaitsev rule. So those are the things you have to mention when you explain the answer to these kind of questions. Okay, that's about that. And so we'll look at a question from last year's paper, 21-22. It says, consider the hydrolysis. So this is important word. So when you sit for the exams, you know, when you read the questions, you have to kind of analyze the question and get, extract given information and try to understand. Sometimes, the information may not be given directly, so it is kind of there. So you have to understand. And so it is given as, the hydrolysis is very important word. I will explain to you why it is the case. Then the substrate is 2-bromo-octane, and it is being converted to octanol in water. So that's also important. So it has been converted to octanol in water. And so they have already given the product. So we know what is the product. So this reaction undergoes, and you get CH3, H, and C. So this is what you're getting. So, and the solvent is water. So then what do we know about water? It's a protic solvent, and it's a polar. It's a polar protic solvent. Because now the question is, identify the reaction mechanism type as SN1, SN2, E1, or E2. So they're asking you to pick which one, what kind of reaction is this? So we have to, so it's already the information is given. So the product is octanol. That means this bromine has been substituted by hydroxyl. So it's a substitution reaction. So definitely it's a nucleophilic substitution reaction. So we know that. So then the question is, so then E1, E2 is gone. So we don't have to worry about E1, E2, because if elimination is happening here, so you would not get 2-octanol. So you will be getting alkenes. If it is E1 and E2 or the elimination reaction is going on, you should be getting alkenes, not substituted products or nucleophilic substitution reactions. And it is in the polar protic solvent. We talked about this in detail, what kind of reactions are promoted by polar protic solvents. And so, because I will show you a summary, then you can kind of pick which one is which. Then they're asking to write the mechanism for this reaction. But before we get to the answer, that's how we kind of analyze the question and extract the information from these questions, given information. So they're not asking to pick, they're not asking, the other thing is, these questions could get complicated because that substitution reactions and elimination reactions are competing reactions. Then there could be some common substrates or reaction conditions where substitution and elimination reactions are happening at the same time, or both are possible. Then how do you how do you kind of figure out which one is happening? But here it is not that complicated, straightforward. Substrate is given, and the product is given, and the solvent type is given, and also it's also mentioned hydrolysis. Hydrolysis means you cleave this carbon bromine bond using water as a nucleophile, or then you replace bromine with hydroxyl. So this is the solvolysis. When water is involved, we call that hydrolysis. So therefore, all the information is given, and so only question is whether this is SN1 or SN2. That actually can be very easily decided just looking at the very easily looking at the substrate, it is a primary, secondary, or tertiary, and also the solvent type. So before we move to this answer, so I have put this table, summarizing this SN1, SN2, E1, E1, I'm not gonna go through the whole thing, but when you have time, you can kind of go through this. There's a summary about these 4 different reactions, because they are kind of competing reactions. Then we should be able to kind of compare the conditions and assess the condition and figure out which mechanism is actually operating. So just to abstract the important stuff like solvent, we know that SN1 reactions are supported in polar protic solvents, because SN1 reaction goes through a carbocation intermediate. First, the leaving group being removed, then you make a carbocation. Therefore, this carbocation is more stable in polar protic solvents. But the SN2 is a concerted mechanism where you have the nucleophile attacking and also the leaving group being removed at the same time. And you have a transition state, no intermediates, no polar intermediates. Transition state, the charge is kind of dispersed. Therefore, it is they are like stabilized by polar aprotic solvents, and so like DMF, DMSO, acetone. But the SN1 reactions are promoted by alcohols, water, especially water. So we have to have protic solvents for the SN1 reactions. Then the E1 also, very similar. So you can read this and study this. You will have an idea of, just to get to see which one is actually operating SN1, SN2, E1, or E2. And the leaving groups, SN1 needs a good leaving group, because the leaving group has to be removed first to create or to make the carbocation. And so even for the SN2 also, you need a good leaving group. But the SN2, the nucleophile has to be strong. So nucleophile has to be strong, because nucleophile, that is the first step. Like that's how the SN2 reaction is initiated. The strong nucleophile attacks the carbon bearing the leaving group, then it pushes the leaving group away, and so then the reaction goes on. But for the SN1 reaction, because the rate is only dependent on it's a first order reaction, dependent only on the substrate, and the first step is to make the carbocation. So therefore, weak nucleophile is enough. So you don't have to, because that's the second step, and that second step is not involved in the rate law, or the rate does not depend on the second step for the SN1 reactions. So likewise, there are many things to consider. And so this all, stereochemistry, in the SN1, you get a racemic mixture. RNS you get because the carbocation can be attacked from both sides. So then it will lead to 50-50 RNS or racemic mixture. By the SN2, you get the backside attacked by the nucleophile. And so then you will get an inversion. So then the mechanism also kind of summarized here, so you can go through that. So those are the like the key features summarized for SN1, SN2, E1, and E2. So again, I have another flow chart here. If you want, you can kind of go through this and try to understand these differences. And some examples for weak acids the weak bases and weak nucleophiles. I told you water is a weak nucleophile, but OH minus is a strong nucleophile. So when When you have a negative charge, so they are strong nucleophiles and they are weak bases. But when you have these, oxygen, and also it is kind of, protonated, so they are weak nucleophiles. The strong nucleophiles are negatively charged most of the time, like cyanide, azide. This N3 minus is called azide anion. The chloride, bromide, your halides, then thiols. They are, even with the protonated thiols, are better bases, like strong, so weak bases, but they are strong nucleophiles. Then the strong nucleophile, strong bases are like hydroxyl is a strong nucleophile, at the same time strong base. Then alkoxides like methyl, methylene oxide, or C2H5O minus, or ethoxide, those are strong bases and also strong nucleophiles. Then we have strong and bulky bases, which would, they actually promote the elimination reactions, because they cannot do SN2 reactions, because if you have steady crowding around the carbon to which the leaving group is attached to, the base or the nucleophile may not be able to reach that carbon to attack that carbon. So in that case, they promote the elimination, because hydrogen abstraction in elimination is happening on the beta carbon. So the carbon next to the carbon attached to the leaving group. So therefore, the steric bulkiness does not really matter for elimination reactions. That's why we have E2 happening even with the bulky, or even with the compounds with bulky groups. So then these are some of the examples for bulky bases: tertiary butoxide, triethylamine. Don't worry about these DBU and all that. So they're not really in your syllabus, but just remember, like, if you have a bulky base, it promotes elimination. Again, another flow chart. I'm not going to go through this, but it's very useful how to determine SN1, E2, SN1, or E1. But for just, this you can use for, like, for complicated reactions. But if you want, you can go through this and try to understand. If not, you can just skip that. Okay, so this reaction, so we know that, as I said, it's the product is given. So we know that we're getting the 2-octanol. And so if you look at the, we got this, sorry, again. So octanol, so then we know that this is nucleophilic substitution, and it is in water. So the water is a protic, it's a polar protic solvent, and we know that polar protic solvents actually favor SN1, because SN1 reaction goes through this cationic intermediate, and the cationic intermediates are stabilized by the protic polar protic solvents. Therefore, this reaction should be going through cationic intermediate. So therefore, this reaction is SN1. So that's no doubt about that. So then the first step would be, the first step would be to be the removal. So then, so the answer is, for the first one is the SN1. Then the second, they're asking for the mechanism. So then you start with the 2-bromo octane, and you remove the leaving group first. That is the first step in here, because you have to make the carbocation first, because this is SN1 reaction. Only one reactant, only substrate is there, because this is first order in terms of kinetics. So this is first order reaction kinetics. And you remove the bromine, you generate the carbocation, then the nucleophile attacks. Here, there's no mention about special nucleophiles. So you have water. This reaction is done in water. So then the water should be the nucleophile, which is a weak nucleophile. We just mentioned that water is a weak nucleophile. And we know that that's another factor to decide this is indeed an SN1 reaction, because weak nucleophiles promote the SN1 type reactions. For SN2 reactions, we need strong nucleophile, because it's the nucleophile initiates the reaction, it attacks the carbon and pushes the leaving group out. But here we have weak nucleophile water, so then the water attacks this carbocation. Then, since water losing electrons, it is now the oxygen is electropositive, and this hydrogen is removed and gives you the final product, the OH. So that is the simple mechanism you can draw. You can write for this SN1 reaction. So now they're asking for the draw a completely labeled energy diagram for this course of the above reaction. So we go back to this reaction, and so this is SN1 reaction, and look at these different structures, different compounds in different complexes you have. So this is your substrate. You start with the substrate, or that is your reactant. And this is your product. So let's identify the species involved in this reaction. And this is your first intermediate. So this is your intermediate. We know that, in the SN1 reactions, we have these charged intermediates or cationic intermediates. And then there's another intermediate. This is intermediate 1. And this again a cationic intermediate. So this is your intermediate 2. So we have to include all these on that energy diagram or the energy profile, the free energy profile. And also remember this, whenever you have intermediates, and then in between this, in between the formation of intermediates, you have to have what? You have to have transition states. So you have to have transition states between these intermediates. So you have to indicate those as well. So likewise, you kind of analyze these, the information given and also the mechanism before we move on to draw the energy diagram. So then this energy profile, so you first draw the axis. So the y-axis is the free energy. So label them properly, free energy, and x-axis is not time. It's called the reaction progress. Reaction progress or reaction coordinates. Reaction coordinates. And then the first thing you need to do is that we know that reactants are at a higher energy level than the product. So then you first put your reactants on the diagrams and then the products. So then you draw your reactant. So your reactant is nothing other than your alkyl bromide, CH3, then Br plus water. So those are your reactants. So this is your substrate, and the water is your nucleophile, and so those are the reactants. Then your product is the alcohol. Alcohol and CH3 plus your leaving group plus water. So those are your products. Then, and we know that you have an intermediate. So what is the intermediate? So I would first draw the intermediate where you have the positive charge, hydrogen and CH3. So that is your first intermediate, but after you remove the bromide. And so then you have a transition state before that, TS1, and this is the energy between the transition state and the ground state of the reactants. That is your delta G double dagger. That is the activation energy. So you can write if you want as activation energy, or put delta G double dagger. Since y-axis has free energy, so you have to put delta G double dagger. So then that's your first intermediate. Then you have another intermediate, which is so that's all I explained before, on the last slide. The protonated, sorry, the positive charge on the oxygens, that is another intermediate. So therefore, before that also you have another. So this is actually, this should be lower in energy because this is right before the product. And after the bromine is removed, and so this should be, and there should be another transition state, transition state 2. You don't have to try to draw the transition states. It may be kind of complicated, but if you want, you can draw the transition state. Then this will go to the product as here. So there'll be another transition state 3, if you want. So because these are, two here also, you lose proton here and give you the last product. So this is the complete energy diagram. And so, and also you can give the, this difference is the delta G naught, or the Gibbs energy change between the reactants and the products. And so make sure, so this is not really nicely drawn because, it's really hard for me to draw on this notepad, but when you draw on the paper, like, remember to, show these shapes, nice shapes. And so that's also important. So those are the information that you have to put here. So if I go through this again, so you put the reactants and the products first where they are, in terms of the energy levels. And then you draw the intermediate. It's in the first intermediate, that you identified. So this is your first intermediate. This is your second intermediate that you identified from the mechanism. Then, well, whenever you have intermediate, so you'll have to have transition states on either sides. Then you show the transition state 1, transition state 2. And these are, the first transition state is the biggest one because it is where you make, break the bond between bromine and carbon. So it's more energy intensive. But then the next step is, the attack of the nucleophile. So therefore that transition state is not that energetically high. So it's a small one. And then the removal of the proton also is, the energy wise, it's a comparatively easy one compared to the first step, which is the removal of bromine. So you have to pay attention to those details as well. So you don't have to like know the values, you just show the magnitude, comparatively, figuratively. You don't have to know the absolute values. This is how you can kind of, show these energy profiles. I hope this helped for you to kind of, understand and also know how to, give an answer for this kind of question, how to draw, So all you need is, you figure out the mechanism, you extract the information from the mechanism and draw this diagram and show the intermediates and transition states where they, where applicable. Okay, so that's all I have to discuss. So I'm going to stop here.